All right, we are starting finally. We are going to, so we've got Chris and Chris here again today, and we're going to actually do a little planning before we get started to figure out what our next step is. So at the end of the last session, we built a little bit of code that creates a sort of set of star systems, and I plotted them out. And since then, I cleaned up a couple of things that I've done imperfectly. So I cleaned that up offline, and we are now ready to kind of decide what to do next. And we figured we'd just start streaming since we're over time, and we're going to use the whiteboard for a minute. So one of the things we need to do, so when we left it, we had a data frame that we'd pulled out from our object model, and we had the same name for all of the star systems. So I pulled out an old piece of code that I had found online a few years ago, which is a Markov word generator or name generator, and I've tweaked it a bit because it needed some improvements here and there. And I don't actually think this is still online, but it's the same kind of algorithm that you can find in any Markov word generator. I've used this module in some of my games, and that's actually why there's a list down here of not safe for work words, because at some point you have to, if you're going to screen user input to name things, you unfortunately need to keep a list of the things that you don't want to allow. So there's a list, there's a static list in there that I check against at the bottom of the module. Okay, well, we won't need that today because we're just generating these things internally. So that's just easily achieved with this little bit of code, which we're not really going to go into right now. So we have a name generator basically, and that's one thing that we could add into the code. It takes a source file, text file, which is just full of, I think it's Roman names and some existing star names, and splices them up and reconstitutes them. So there's 50 names right there, which are kind of, yeah, they're kind of cool, some of them. So yeah, that's one option we have today. Another option will be to talk about the geographic distribution of these star systems a little bit more, and think about whether we want to impose any kinds of patterning on that, or just to leave it essentially Gaussian the way it was, and let the structure just be a little accidental. And we could also talk about improving the types of data that we can produce from last time. So we only really built that float range model. There are other types of stochastic data that we could generate using similar constructions if we just want to keep going down that rabbit hole. So yeah, what do you guys think? What feels like something interesting to do today?
So I think it might help us to start at where we need to get to, and you can work back from, like, we have stuff that's good enough for some things, right? Mm-hmm. And we could certainly work to improve those, or we can move on to the next big thing, and then come back to revisit whatever isn't shiny enough at the end.
Yeah. So that leads you to think that we would look at the geographic stuff, because it's different.
Yeah, let's go broad strokes first.
Mm-hmm. Well, so we have, I mean, this is essentially already a map.
Yep.
The question is, I guess, do we want to put some imposed structure? Like if we're running this as a hackathon, some of these, I guess it's going to depend on some of the rules that we create, right? Because some things will travel between star systems, and if they're Gaussianly distributed like this, then there's the potential that some will be too far apart for anything to happen. Maybe that's okay. Maybe the outliers, you just learn that those aren't the ones that are relevant, yeah. Right? So we can potentially keep those.
What would be great is if there was some threshold of other properties that made it relevant again.
Mm-hmm.
So outliers amongst the outliers.
Mm-hmm. Sure. That's right. And that's potentially some of the properties that we'll end up designing.
Yep.
We might add additional variables that influence that.
So do we need to talk about the models that we might use first to know where to go, or do we need to?
Yeah, I mean that's one of the things we could talk about the logic of the incidents that we had begun,
Right.
and that's related, I think, to.
Just looking for something to grab onto to see it right. So.
Yeah. So we talked. Let me move this over so it's visible. We talked about a kind of plague type of model for fun to get ourselves thinking about these things. So we had the idea of a probability of infecting a planet from another planet. So
can we do that just flat based on distance?
So I think the idea would be that there would be it would be like die rolling, right? You draw from a probability distribution that is biased according to how far apart the two worlds are.
Right. What I'm saying is, can we just go ahead and run that with the Gaussian distribution to see if it is like going to trigger enough to matter?
Well, that's right. We would definitely do that. Yeah, we would come up with some parameters and we would test it against that data set that we've already made and see, what are even potential transfers of that to see if the parameters are reasonable, and then measure some statistics about that. So
if we want to tweak the geography, then we need to know whether it needs tweaking.
Right.
So that might be a sane starting point.
Mm-hmm. And it'll be a precursor to any other type of things that will happen between two of these objects, right? Because there's always going to be a probability of something changing based on the properties of these objects, and this will be a good starting point. So we thought that we just came up with some ideas. So, for instance, we were going to have like a necessary condition might be that you need at least 75% water surface coverage. Just make some stuff up, right? So we could attempt to sort of reverse engineer with some of the data that we created last time how many planets have that property right now, and then come up with a probability distribution for the transfer.
How many planets have that trait within certain distance of another planet that has that trait?
It would be. I was going to not make it a cutoff threshold so much as it's a soft threshold where the probability is like linear even with the distance.
Did we? I guess when we're generating the planet generating objects, did we already set those attributes?
Well, we had. I think we made a generic. We made oxygen percentage, so we can just use that as a surrogate for now.
Okay.
Yeah, we should probably build. We didn't really need the whiteboard, did we? We should probably build a diagnostic tool that helps us measure from the object model or from the data frame. Maybe the data frame is actually better, and extract some statistics on any of the attributes that we care about. Something that I haven't brought up on my system is the chat room on Twitch, so I should do that.
I'm looking at it too.
Oh, you are? Good, thank you.
Okay. So spread diagnostic.
Okay.
That's just going to be based, so simply on proxy.
Oh, see.
Oh, you killed Seedon.
I know, I did it again. I'm sorry. There we go.
There we go. Let's see if it's readable.
I can temporarily make it bigger.
Oh, good. Nice.
Don't really need me in the picture. Okay. So could you read that out just so it's...
Yeah, so we're going to work on the spread diagnostic based on the proxy attribute of oxygen. It's going to be a linear spread on distance.
Oh yeah, right. Sure. So yeah, the first thing then is that we need to measure the statistics of the oxygen levels of all the planets. Now the planets, I guess I'm thinking back to what we've made. This table that we made is for the systems, and it only has planet identifiers. It doesn't actually store any of the data about the planets themselves.
Okay.
So another option is to...
Can you shrink the...
Oh yeah. Thank you. So this table only contains the data about the systems, not the planets. We never made the sort of system to table transformation function. So that's possibly boring in a sense, because it's going to look a lot like what we already built, and I could do that offline.
Okay.
But we do need the data from the systems. I could also just iterate through them manually, kind of just in line.
You know, it's not boring.
What
is the systems that there's if you scroll back to that system map.
Yeah.
Okay. Yeah. So and I'm not sure on all the capabilities on Matplotlib to do this, but what if like just for background on the way these planets, the way these systems are generated, they can have from 0 to 9 planets, right?
Something like that. Yeah.
Okay. But what if we either varied the size of the dot by the number of planets, or this is where I'm uncertain, is where what if we put a ring to represent the orbit around each planet?
Oh boy.
Too much? Too much?
Well, so you have to remember that the planet orbits are all going to be at a scale that's far tinier than this scale that we're looking at.
Yeah. But it's just it would be quite to visually so somebody looking over.
Why don't we get our model down?
Yeah.
And then switch over to visualization, right? Because it feels like we're going to be shoehorning.
Yeah.
This on top of this thing. It's really. Is that fair?
Yeah.
Yeah, I do like the idea of changing the marker size to give you an idea of where those planets are, and we may also color code them according to, say, an average oxygen level across that system or something like that. There might be some useful traits helping us design from that. So yeah, some of those things we can come back to.
Cool. I think at the end that's going to be like crucial for the general polish.
Yeah.
Okay, so we are going to want to iterate through the system and actually extract the oxygen levels. But I guess we want to be able to visualize them too. Yeah, thank you.
Just a little bit more down.
Yeah.
Oh, it works.
Yeah,
of course you're there. You're on live thing. I'm seeing a delay.
Okay, so we have
Like this if I need to.
We have a universe object, which I think I may need to rerun all this.
Because I can't see.
It's slow.
Chaos control. What you trying to do?
It's where I can adjust this easily without bumping into stuff.
So just rerunning our notebook, get everything live again, and fix the camera angle, because we're still learning how to do that.
Yeah. We're just meddling. I think that'll be good.
All right, so now we have a universe object, which is a list. So for every system in the list, we need to pull out some stats on the oxygen levels. So on one hand, we could do it per system, because the distance across the star systems, we haven't assigned like a physical distance. We've just assigned an orbit number, right? And so we could treat them for now all the same, just in terms of integers. So we could look at like the relative probabilities of things jumping per system. So I guess let's to break this down, let's pick a system, and let's look at the planets. So that has 3 planets, which is great.
Do we need to care about planets first go around, or can we just do systems?
It depends what question we're going to answer.
Okay, so it feels like it's a prerequisite of spreading to a planet to spread to a system.
It does. So I think the base case might be you assume it's somewhere already in one system, right?
So
the very, very like 0th step, I think, is to just assume that this is the system that has something in it that we care about. And
just want to pick something random.
Let's pick our first planet out and remind ourselves what we have in it. So it has an attribute which is the oxygen percentage, and that's 74%. And so if I want to see them all, I could write a simple loop, and I can do a list comprehension. So actually, let me do some naming here just to make things a little easier. Let's make a test system, which is the first element of this list. And I don't need this anymore, because that was just testing. So Alright, so we have 3 planets and none of them meet the criteria. So what we're going to probably have to do is run a loop to at least, or actually we can set the threshold wherever we want, can't we? So we could just say the threshold is 50%.
You just pick the one with the highest.
Yeah.
Just max oxygen, whatever.
Yeah. So for giggles, we just set this to be 50%. And that's our, that's the percentage threshold to even be susceptible. So the model that we're going to try to think about really is it's called an SIR model. If I remember correctly, it's a model from epidemiology, and it's about spread of disease through a population, and you treat the individuals as a network. So each individual can be susceptible or infected or recovered or removed, actually, it may be. So once they've been infected, they're removed because they've either died or they've become immune, and so they're no longer susceptible. You can have models that regenerate and bring them back into the susceptible population depending on what you're modeling, but that's the simplest form of it. So I guess we're kind of thinking of a similar model here. So you've got the planets are the potential susceptibles, and you're going to be susceptible if you have an oxygen threshold above, in this case, 50%. And then you have a probability, maybe at each time point, of being infected, depending on your distance away from another infected planet. Okay? And then you would, if you sort of draw from that distribution and you meet the criteria on that turn, then you become infected, that planet becomes infected, and then on subsequent turns that planet is now able to transmit itself to a further planet. And you can build in an incubation period, you can have all kinds of rules like that if you need it. So I guess I just wanted to start thinking about the spatial distribution model. So we're going to say that the probability changes linearly with the distance between planets, and so we want to set up something that is so we haven't really talked about the time units we're going to have in our histories, but I actually think it might be fine to have different time scales for different types of measurements.
Yep.
It's easy enough.
Makes sense.
Because they're all in different tables anyway. So this could be on a time scale of weeks or months. Right? So let's say it's weeks for now. That can give us a mental idea of what's reasonable numbers to be coming out. Because you don't want things to spread too easily, because everything will just saturate within a couple of months, and vice versa, right? So you've got to tweak that.
And the Federation uses hours for everything.
Yeah. Well, we can make it more detailed if we like. But again, it's just, it's sort of arbitrary right now, just to get a feel for getting the models. And so we're going to want a linear model, and any linear model is going to look like that, right? It's y equals mx plus c. And in this case, the output is going to be a sort of probability or probability factor that is controlling the likelihood of transmission between two places. And the dependent variable is the distance. So let's rename that to be prob and this to be distance. And then we want to have the scaling factor, which is your m. So I guess you have to think, if the distance is 1 unit, what probability do you want to have of transmission? So in this case, you're going to assume that the first planet is infected and the second planet is not. And if they're a distance of 1 unit apart, what probability do you want to assign for that event, for the incident, for it to transmit?
Is 1 unit the lowest number of units?
It would be, yeah, in the current model, right? It's like one orbital position different. So the orbital positions don't have real distances associated with them, they're just these positions, these integer positions.
Necessarily be very high, right? So 95%.
So this is an interesting problem that comes up when there's a difference between an eventual probability and a moment-to-moment probability.
Totally.
Right? So yes, you might hope that whatever model you use, when you draw from it over a long period of time, you will have achieved that 95%.
Right.
But on a time scale of weeks, you need to kind of divide that down so that that becomes likely.
So we do a probability of a small number on a week-to-week basis, but since there's a high number of weeks, then your district probability.
That's right. So that's a common thing to work out in a game that has time associated with it.
So we kind of need to know the lifespan of the pathogen.
That's right.
Yeah.
That's right. So if you want it, so 95% in a sense is it only becomes meaningful once you determine a time scale for that to be valid on.
Yeah, because if it was 95% on a week, then guaranteed, like two passes would.
Exactly. So again, this is all open for discussion. We can start by saying that you might imagine that you would expect there to be a 95% chance within a year that has been transmitted.
So we've been talking about the total number of years of data we're going to generate is 50. Is that correct?
Again, as a starting point, yeah. Although, actually, I sort of changed my mind. Maybe if we do open it up so that different types of data can have different time histories. Because it's possible that we'll need much longer history for some things than others in order for them to be useful. So those could be potentially hundreds of years for certain things.
So I guess the total time history of the spread, right? Mm-hmm. How many systems total are we kind of soft targeting?
I think we'd talked about maybe having it's in the thousands.
Percentage-wise, what is that?
Oh, of what? Sorry. Oh, that have planets, or
no, that you expect the spread to reach a certain number of planets or systems.
Oh, I see.
Right.
Because
then we need to figure out what.
Sure, you can back out some stuff from that. Good question. I guess we don't even know yet.
Okay, so let's make something up. So let's say you want to do 100 years, so it's round.
Okay.
So we're going to go for 100 years. That's going to be...
Spread.
That's fine. Cool. Alright. Now we're going to look for 50%.
Sure, let's start with 50.
Cool.
Because you want plenty of threats left over to...
be wrong. False positives.
Yeah, false positives, and if it's 100%, then you're done already.
We can go lower too if you want it to be harder to pick out. You want more.
Sure, but it's a parameter, so 50 is fine for now.
Okay. Cool. All right. So then it feels like the next thing is we want the total length of kind of the length that it's going to take for a system to succumb.
Yeah.
So maybe that's 5 years. 2 years. We're gonna have to model it to see what it actually looks like.
Exactly. Yeah.
It's gonna take something to start, right?
Right. Yeah, we could say 5 years
5, 2,
and just see how it feels.
Okay.
Yeah. So I guess that would be an average that we would try to hit, because some systems are only going to have a couple of planets, others are going to have many planets.
You could splay on that based on the stats or the proximity, number of planets, same thing.
Right.
Okay. Cool. So what's
Just to let me make sure I understand. So 5 years for systems to succumb. That means that if any one planet in the system is infected, then we would expect it to.
So that's what I was just about to ask. Is there any way for the pathogen to peter out? And
There could be.
so let's pass on that for now and
Yeah,
just
let's pass on
assume
that
that
for
it's 5 years and done, right? So 100% mortality rate after 5 years, right? Good.
Sure. Yeah.
Like 100% mortality rate for an entire star system.
Yeah.
Okay.
So after 5 years, done, right?
Anything that's susceptible is done.
That's right.
Cool.
Yeah, and that's just obviously not going to be what makes it end, but just to start somewhere.
Yep.
Cool. All right. Grim dark future. All right. Okay. So what does that tell us? Does that tell us anything? I don't think it tells us anything.
Well,
May I ask what it tells us? Yeah, it looks like so. What we're looking at is what the spread of the Vanta Black Plague looks like after 100 years. So we start off with, I guess, some level of seed planets that have it, and then we kind of. It looks to me like you were working, like you're setting something up that we could work backwards.
That's right.
To see if. Like we work backwards from if we want 50% of planets infected by infected after 100 years, then we want to see what the we work backwards to get to our starting point.
So what we don't have, So what we don't have yet is the percent transmission rate based on that 5 year period.
yeah. Yeah.
But we can get like we can derive that by like taking the number of weeks in those 5 years, and then we develop it was pretty much a Bayesian thing, right? Where we're just adding the probability, like we just figure out if we choose a probability that adds up to that amount.
So there's a lot of dependent stuff based on proximity, right?
Yeah, I don't think it's a Bayesian model. I think it's easier, that's simpler than that. I think they're just rates. You just think of them as rates.
So we just, but we'd ultimately choose a rate that, we could we just get to that rate by taking the number of weeks and then dividing the, dividing it by that.
I mean, that still comes under some assumptions that, I mean, yes, that will give you something on a system-wide level, but on a planet per planet level, you still need to sort of titrate it based on the actual distance.
So what if we start with so just for the system itself, right? So what's the curve of infection going to look like in a system itself? Because that's going to drive how infectious it is, right? So the number of infected population is going to drive how infectious the system is.
Well, that's right. Right. It will zoom up. I think what we kind of need is we need a little system to be able to play around with it. So let's build a little bit of code that lets us simulate the weeks, right? So
always the best.
It's my favorite.
Oh, cool, thanks. So what we are going to have is a range of weeks and that is simply going to be a range. We'll make it might make it an array, and we're going to have 52 weeks times 5 years is going to be like the time span we expect interesting things to happen in.
So that's the time span that we're going to have the 95% in, or whatever.
Yeah, so we're going to say something like 95% saturation of susceptibles in this in 5 years, or 52 weeks.
Hi, people.
Oops.
Oh, nice.
So there's your array of weeks, and so we're going to assume that they're one planet. So we'll start out with an infected planet 0. Okay, so we need to iterate through time, and for every unit of time, we calculate the probability that something changes. Alright, so we'll say for week in time. I could have called that weeks or something. So for each week, we need to generate a probability. And so first of all, we're gonna need to roll the dice. And so we're gonna take a random number generator, and that is, I think it's random. Yep, number between 0 and 1. So that's essentially your die roll. And then we will check a value from that against some threshold. So this is per planet. Okay, so we also need neighbor planets. So I need to iterate through our test system's planets.
It's just weighting based on the infectional neighbor.
Yeah. So we have a neighbor planet, and I also need to know how far away it is, which currently is just the integer difference between my location and its location. So we're going to enumerate here. So we'll just call it I. Oops. And we'll enumerate the planets. Okay, so obviously I'm not going to reinfect myself.
Right.
So I need to know my own I need to know my own position, and so we've set that position to be 0. Okay.
So there will be like a percent infected rate, right? So like if you're infected, that's just kind of a Boolean. But if you have the last, like the death throws, right?
Sure, we might make it more sophisticated. Yeah. Don't forget we have to not test self, so we'll skip that. It's a cheap way to do that. All right, so we're going to have this distance surrogate being the absolute difference in the subtraction of my position and the position of the other guy, the other planet, and then that's going to feed into our model. Okay, so that's going to scale according to what we had up here. So I'll actually reuse this. And so this isn't a probability yet so much as, well, it kind of is, I guess. So M has to be scaled according to these weeks. Something we might do here is divide by 52, because we kind of want it to be built in as a kind of weekly thing. So we just need to think about, if the distance is 1 and this is happening every week, what should M be to give us some kind of sensible values, and what is the minimum probability? So C will give you the minimum. Well, actually, yeah, so really it needs to be distance minus 1, because that will give you your base case of at the smallest distance, what is the probability? And that's coming from C. In fact, we might divide the whole thing by 52. We'll see. See how we go.
Flat probability.
Yeah, what's that flat probability? Well, I guess it's what is the probability for the closest planets per week.
Right. But
Okay.
no scaling on that, just
I mean, the scaling, right, there's no scaling on that. So we could say that, and we can set this outside, oops, that might be something like, on a weekly basis, if they're, we actually, so it's inverse, right? So the probability is less with greater distance.
right.
So it's not exactly a linear model per se. It's actually, we might reciprocate this, in which case I'll take away the -1 so that the base case is not dividing by 0. So when you're closest, the distance is 1, and this is the sort of place you might comment this, closest integer distance is 1. But now you still have, now the base case is going to be m plus c, which is fine. So, but we have to take that into account.
Looks like you just got a question about the music.
Oh, really? Nice. Okay, that's great. It's, I'll put a link in later, but it's my alter ego Ripple County Primary, and you can find it on Bandcamp. So let's see how easy it is to pull that up. There it is, right there. So this is a few of the tracks that are playing right now. But yeah, thanks for asking. Sure. Good idea.
What was that? Oh, posting the code. Yeah.
It is, right? Why make them suffer? Thank you. There's about 20 tracks on this playlist which cover other demos and things that aren't on that, just so you know. Okay, so base case. We should have maybe, let's try a weekly base probability of, so we wanted to get coverage within 5 years, so that's actually quite a long time, so we don't really want the weekly probability to be very high, right?
So we start with just making it flat, so just divide 95% by 250, whatever.
Okay, let's see what that would be.
60.
So it's over 52 times 5. So that's 0.3%. Now, the other thing would be, we have to remember that m will play a role in this as well. So we'll probably even reduce c further. Because, for instance, it might be the addition of those two, c and m, if one is... I need 2 zeros in that. Let's make this a little bit bigger. Alrighty, so let's see. Difference. Yep. Good. So what I should do is make that a function, because then you can actually see it played out. Okay, so
just for the listeners, does this kind of play into the third law of probability? Basically, the probability of an event happening is equal to the sum of the individual probabilities.
Oh, well, not really, no, because we're not adding probabilities of separate events. So if you had separate events that were independent, then the probability overall would be the sum of those probabilities of something happening. But this is just generating essentially a linear distribution for a single event. We haven't yet. Oh, I guess maybe you're asking about
Like
when
each week is an event, basically.
Each week is an event, and I do also have a loop in here over the different planets. So there is the possibility of having multiple events in the same week if it so happens that one planet spreads to two.
Yes.
And then
that's a good point.
then at the system level, you're looking at the sum of those probabilities as independent events, assuming that we keep them independent.
So we really get to test that law after we've created the loops.
Well, we'll just use it.
Yeah,
we'll use it. Okay, very good. So this is a function of distance, and I'm going to hardwire. I'm going to pull these common things out for the model and put them in as constants here. I think. Yeah, because they're parameters we might play with outside of the function, and then I'm going to return. Oops. I'm going to return my probability at a weekly level like that. Okie dokie. And I don't want to call it prob anymore. Okay, everything is defined. Infect prob. So you would test this, for instance, so that it's a really small probability at a unit distance. Because we're dividing that by 52. Oh, I guess we already divided it by 52 up here, didn't we? When we were... so yeah, we kind of doubly divided it. So I'd actually consider dividing by 5 years. And... because we're already dividing by 52 in the function, and this will make the numbers a little bit larger and easier to think about. So these are now, over the course of the 5 years, more like 20%, and we might split that 20% between the sort of sort of curve it a bit. So maybe 10% of that you get immediately from 10% of that is a given, and then the other 10% scales with the distance.
So this is another thing that we can parameterize as we add into the actual production of the game.
Yeah.
So maybe like the shape of, you were talking earlier about like the incubation period, things like that. Maybe that changes the shape of this curve, right? So maybe it's 20% for the first year and it goes dormant, right?
Mm-hmm.
So like it's infectious originally, but then it like is dormant for a couple of years and then it spikes up, right?
Mm-hmm.
So it's also even for curveballs to people trying to figure out how this thing spreads.
Sure. So we're going to say that the target is, and I'll copy this down to be a bit more explicit about what we have. Oops. Okay. Alright, so we have a model, and that generates your probability. And just to show that if you put in a much larger distance, then that probability's gone down significantly. Right? It's scaling linearly. And if you really want to see how it scales, and if you want to like play around with the function properly, you would sample it and plot it. So you would maybe make a list of. So the minimum distance is 1, and the max we said is max non-planets. And we can plot the samples just against D, which is already an integer, and that'll give you an idea. I'll put a semicolon here, we don't need the output. Give you an idea. Oh, I need to move the window, it's not quite visible. Let me move this back over. Cool.
Yeah, that'll do it.
All right, so you start off with a 0.3%, and at the largest, actually max non-planets, that should be +1, because Python ranges are not inclusive. Okay, so the 9th planet out has So it's not that much lower, right? So you might want that scaling to be quite significantly greater. So one thing to do then is to...
it's also assuming we keep the distances fixed based on...
Sure,
right?
Sure, which we might come back to, yeah. Right, you might actually allot a whole set of positions, just integer positions, and assign your 9 planets across those integer positions.
So for now, assuming, like, that seems like something we'll almost certainly want to change.
Mm-hmm.
Could we have it where it just right now maps, like, the number to a distance, and then we pull off the distance, and that way when we want to change it in the future, we can?
So you mean...
So right now there's the planet number.
Yeah.
And let's just assign that planet number to another variable that's distance, right? And then when we want to change that in the future, we can just stop assigning that over.
Sure.
Right.
Sure.
And that way, what I'm getting at is right now we don't want to have this scaling tied to the position number and then have to change it.
Sure.
Right.
No, that's absolutely right. The fortunate thing right now is that they're both integers.
Yeah.
And so this function is valid. You know, you can test it by putting in, if you say had 100 positions as for orbits, then you can see that this drops down over that 100 positions to the baseline, which is essentially your C divided by 52. Is that right? Yeah, I think so. Right, because yeah, C over 52 is what this will asymptote to. So you have to decide at high distances, is like a 0.2% chance every week. Is that fine at large distance still, or do you actually want that to go away? Maybe C needs to be very small, right? Maybe as distance gets very far, you don't have a baseline probability anymore. So we may want to move C much smaller.
That's where we start running into narrative, right? So like, is there commerce between these systems?
That's right.
That's a good point.
That's right. So there's a lot of other aspects. But anyway, we can see where these parameters begin to play with the narrative like that, which is pretty interesting.
Because 0.2 is actually really high if you think about it. Like if you're thinking about it, if they're not in adjacent orbits.
Yeah, well, it's 0.2%. So it's
0.2, but even that.
But it's still per week. Yeah. Right. So now we sort of rescaled that. So now the probability gets down to 0.0. Wait, no, that'd be 2%. It's 0.1% now. Anyway, that's good enough to start playing with.
Yeah, for sure.
Okay, so we have that. We just need to get something running to begin with, right? So for each week and for each non-me planet, I need to generate the probability of the transition event, and so I'm going to call my infect probability now and test that. So you would generally, your test is whether that probability is below your random number generator.
Right. Just susceptibility.
Yeah. Right. Is that true? No, I'm doing it. You want this to be the other way around. You want because if the probability is small, then you want your random number generator to be smaller than that number.
Right.
Okay, so this would be for the event to happen. So this would be infection
We
event.
want the susceptibility to have to be. Yeah. Okay. Yeah, you're right.
And we haven't tested the planet's oxygen level yet. Okay, but we will add that in afterwards. First of all, I just want to see if we even get these events happening. And so we'll need an output. What we do need to test, we need an attribute to say whether the planet is infected. So the easy way to do that would be to make an array, or we'll just make an array of zeros for P in the planets, or we can make that false, stick to booleans, and then we'll be saying if infection event is true implicitly, then first of all we would update the infected status at position I.
Are you? So there's a 0th planet.
Yeah.
Okay.
Yeah, and for now I'm the 0th planet, so you would force that into there just if you want it to be consistent by setting that to be true. And I wouldn't use 0 because I've already given it a name. It's my pos. All right. So first of all, yeah. So we don't want to test for infection if it's already infected. So there's a conditional on any of this, right? And then we will, so for later, is the planet susceptible, so oxygen over some threshold. So we'll come back to that. And then we want a time course. So first of all, at the end of the 52 weeks, we want to see how many of the planets are infected. And none of them are, so we need to figure out what we're doing. Okay. So we can add some diagnostics in here and understand. So we kind of skipped ahead, right? Because we didn't really test stuff as we went. So I'm just going to print this probability that we generate, and
when you're prototyping like this, do you ever, go TDD route, or you really just use the notebook as a way to?
Yeah, I kind of use the notebook when I'm feeling sloppy like this. You can totally make some tests. In a sense, we're even writing a test now because we're trying to. It's not a software test; it's a systems function test, which is that we want this 95% property, right? So we're gonna say. I'll create another variable here so I can print them out. Just make sure we even get into this loop. All right, good. So what am I doing? So these are very unlikely events. Those were, am I not thinking about this right? Were these?
It's weekly.
It's weekly. So there's my probabilities drawn from uniform distribution, and there are my. These are constant, I guess, for each planet anyway. But yeah, I don't think they're big enough.
Cool.
So, because nothing ever happened. So we'll keep an eye on that. I think I might be missing something in my thinking, but we'll scale these up a little bit.
Yeah.
And actually, that's well, no. Did I run it over all of the years? Yes, I did, because I made time to be.
We're talking about 20% for a year. Did that get put in there somewhere?
No, we haven't brought that in. Let's just increase these and see what happens. Let's at least see something get infected. This is still quite small. I guess because we're dividing by 52. Yeah, sometimes you just have to hack in some numbers until you can get something to work, and then you can kind of look back and figure out what happened. All right, so everything's infected now, so that's good. So we kind of we can use this empirically to figure out what good parameters would be. Now that we can even create an optimization, right? So if you want a target for across many systems, you can loop over some combinations of C and M until you generate data from the simulation that has the right statistical properties. And that's just kind of a cool but dumb way to do it, because then you don't have to necessarily figure out from first principles what is the right model. You just use the fact that you have a target that makes sense to essentially brute force the parameters that will give you what you want.
The gotcha there is that you stop at knowledge and never progress to understanding or wisdom to know what happens if it breaks.
That's right. Now, on one hand, you still have an opportunity to go back and introspect why that is the right choice, especially if you're really stuck in the theory and you just can't see it. You can brute force it and then, like, retrospectively figure out what you were missing. That can be a good way to do it. And if it really doesn't matter and you just need it, then that's also a kind of a quick way to get the answer. Because optimizations like this are super simple to set up. We might even do that as we.
That'd be worthwhile.
Yeah, I think it'd be kind of fun.
Yep.
So I'm going to take out this print statement, and we've just done this for one test system. Okay, so we want to build in maybe the susceptibility first. So let us check. We'll add another if statement. So we have a planet object called neighbor, and we built a threshold earlier called oxythresh. And so all of this is predicated on being susceptible. And so what we should find now for this particular system is that only the last planet got infected, because the middle one isn't even susceptible. And of course that's not a proof because it was a probability model, but you can run it a few times and it will continue to be the case. So that sounds good. All right, so that's another parameter that we might tweak, is that threshold. All right, so and I do encourage questions, so if we do have some viewers, if folk are interested to explore something that I haven't made clear, please let me know. Okay, so we kind of need to do this across all of the systems. And I guess our target might be to, well, we don't have interplanetary spread right now because we don't have any...
Intersystem?
I'm sorry, yeah, intersystem spread.
Do we even have a distance? We don't have a distance established. Oh, like we have a visual, but
yeah. Well, yeah. Well, the distance is we'll just use Euclidean distance because we're treating this as a two-dimensional system for simplicity. Mm-hmm. We might have to have a secondary event type to transmit between systems, like a wholly other kind of form of transmission. We haven't really thought about that yet. We were potentially having active agents, right? These extraterrestrial folk who might be doing something. So that could be a reason for things to spread between systems.
Perhaps if we, this might be too much for now, but if we have some model that says that these are the planets that this planet is commuting with, and then they're... Yeah, so we may have some records of communications. The time series data would just show up as some measure of trade between planets.
You can see this like getting up into a crazy town and mapping entire economies and being like, what?
Yeah, right, step by step.
Yeah.
Do you want to rotate that round between you again, since you're
Sorry.
standing up?
People need to hear Chris more than me.
So I guess we've just done this for this one test planet. We could look at the stats across all planets in aggregate, since we don't have any other real way of talking about the systems together. So what we're going to do is we're going to inject another for loop in here and loop over all of the systems. We can still call it test sys, since we are testing this system. And we've got this universe, which is a list of all of the systems right now. And we can just... The pretense here will be that the 0th planet will always be the infected one. Or we could pick a random one, actually. Why don't we do that? So there's nothing to do if there are no planets.
Right.
So if the length of test sys.planets is 0, we'll just skip. And then I want to have...
Yeah, see, that'd be neat too, to, like, as we go, even systems without planets, you can have, like, asteroids you can mine.
Oh boy.
Yeah.
Yeah.
Bit by bit, bit by bit.
Yeah.
Initially infected planet.
We're just rescanning Dwarf Fortress.
I love Dwarf Fortress. I can't believe that was created by one person.
Yeah,
Originally.
nuts.
It's completely nuts. Okay, so I want a random integer between 0 and the number of planets. May as well just calculate that one time and make that a variable. So if there are 5 planets, yeah, that will be correct, because then they'll be numbered 0 to 4. So I'll pick a random integer for my initial position, and I've got... And now I need to make this infected list dependent on... Ooh, that's a little trickier. All we really need to know is how many planets overall in aggregate, so...
Per system or total?
Total.
Okay.
I mean, we might need both. So what we'll do...
Would it help to aggregate at system level and then have that
We could.
kind of a roll up from planets?
We could roll it up, because we'll probably want to know both.
Yeah. I don't feel like there's ever going to be a chance of, like, at the current state, we're not going to model spreading from a planet to a system, right? It's going to be system to system.
I don't know. That's a good question. No, that's a perfectly good question. We haven't come up with those mechanics yet. But yeah, for now we just want some insight into these kind of probability models, how they're going to shape up in a very, very simple way. So yeah, I agree. Let's just build a running. So what I just built before was a representation where you have a list that always has true or false for every one of the planets. This is going to get a bit more complex now, so I guess what I'm going to do instead is I'm going to have a list that isn't preset in its size, because a priori we don't really know that doing this loop. I am just going to append the planets, the count of planets that are infected. So we would need to, you know what we need for this? We need the name of the system to be different, so that oh no, we don't. We can use the integer for that too, because we have a position in the universe list that we'll have to do for our unique. All right, so we have a system number. So we do know how many of those there are. And I'm trying to think. Yeah, I can multiply that. It's a little trick in Python. I can make empty lists. There's a default. There are some nice data structures in collections to do this stuff probably better. But let's have. Oops, I'm sorry. Okay. So that will give you a list of empty lists. That way I can always append the planet number that gets infected to count them. Do we care which planets it is, or do we just want the count of them?
It feels like, yeah.
Yeah, well, there can just be a count. There can be a count.
Yeah.
So never mind. We will have...
And it feels like we're not going to even really want to count per se, because we're ultimately going to want to know how infected the system is.
It's like a density of...
Because all this stuff is going to be basically thresholds, right?
Sure. So it can be, yeah, that's probably true. So we'll make it 0, and then we will divide. We'll make it a fraction of the.
So just add up all the percentages infected and then divide by number of planets.
Yeah. Now sometimes you need both the absolute and the relative.
Sure enough.
So we might even record both. So this is really looking like a NumPy array instead, and we'll make it zeros, and we want it to be of length the number of systems, but dimension of 2, because one will be the absolute.
So why are you switching data structures there?
I'm switching data structures because this zeros factory function is just so much easier to build an array than composing these sort of awkward constructions with lists. Plus it will let you do some tricks later with pulling out the rows with sort of slices. So absolute. So we're gonna record the absolute and relative density of per system infection, assuming every system with planets has one infected planet. So this is obviously just a very basic test.
And we're hoping to see.
Well, we want to measure over all of the planets the saturation and the density that we get, because this is also going to relate to the oxygen percentage or whatever other threshold we have for susceptibility.
Right. So we're hoping to hit that 50%.
Yeah. Well, that might depend. What was that predicated on? Was that 50% based on spreading over? Yeah, that was inter-system spread.
Yeah.
So we don't have that model yet. So that 50% is not yet a target.
I think we were using the inter-system spread as a proxy for planets, right? Because we really cared about how many targets they had to sample.
Yeah, because the goal in this game, well, part of the goal would be in this case to look at time histories of previous infections and predict the most likely planets that will get infected in the near future and flag those. Right, that will be part of the object of the game, is to detect those, to predict those.
And right now, the model that you're working on is just assuming that every system has one infected planet. And we're just going to see what.
Yeah, because once we start to understand the statistics of that and how the parameters affect that, then we can remove that assumption and then allow, as time progresses, to have inter-system events.
Yeah.
Right? But we just do one layer at a time just to get used to the numbers and make sure that we're not saturating everything too quickly or making nothing happen.
All my friends are dead.
Yep. So let's see how we're doing. So I've assigned. I have made it a bit more interesting. So now there's an arbitrary planet is selected per system, and I've added the threshold for the oxygen to be susceptible. We need to. What else? Oh yeah. Now I need to actually record. So what I did before is I recorded in that array. So what I need to do now is count. Oh, I see. Right. So before I was detecting whether this planet was infected. And of course, I still need a record of which planets are infected. So the counts aren't even enough. I still need a data structure. Now, fortunately, and I might just do this as a quick hack for now, the planets are objects that we created up here. And so we could actually go all the way back here, and for a planet we could create an attribute.
I've got an aside here.
Yeah?
I posted this on Facebook, so we're getting comments outside of Twitch.
Okay.
My buddy Greg from Birmingham, he says, assume rate of crop production per acre to feed population with fixed birth rates and lifespan as a function of food supply.
Yeah, you're with me, Greg.
He said within a few generations you won't need plagues.
Right. Nice. Nice. No, I would totally, you can totally take these models to that point once you've felt out how to layer these things up. I mean, the whole the whole difficulty in balancing games is you introduce new factors, and a previously balanced game can rapidly become unbalanced. And you even see that in Fortnite, right? Like,
Emergence.
yeah, you get emergence, and you introduce a new thing, and it shuffles everything around in subtle ways through emergence.
The meta is just really a commentary on what the emergent predisposition of the game is, right? Like that's all it is what is the most optimal strategy in the moment based on the factors you've introduced.
Mm-hmm. So I need to rebuild the universe so that the planets all now have these infected attributes, and that way I can actually, instead of testing a position in this list, which is a pretty crummy way, this is actually now something that I can check directly from that attribute. So now I will be setting that attribute when we have a successful infection event. And now I can record the stats as I go. So here's the instrumentation. I will be indexing the NumPy array based on my position in the system. Oh good, I was going to tell you could fix that. Okay, so we've got, we're going to have the absolute number increased by 1. So this NumPy array creates an array of zeros, and the absolute count will have just gone up by 1. So the 0th positions is a two-dimensional array. The row is given by the system number, and the column is given by 0 or 1, depending on whether we're addressing the absolute or relative. And then the relative is at this position, and it is equal to the simple way to do it is honestly just count the absolute number and divide it again by the size of the system. So it's the count of infected divided by the number of planets, which we've already defined. All right. So because we ought to test that we're doing this correctly, let us print out this every time there's an infection event, and just to make sure that we don't put too much on the screen, let's just run this over the first 20 weeks and hope that we get a couple of events. And we did not. Okay, so something's not right yet. Oh, wait, that thing is really long. I could have done with putting that in the other direction. All right, let me see. Oh, well, actually, no, that's fine, because if we're inside of this conditional, then there was an infection event. So, let's see. Let me kill the output on that so I can bring this back and look at all of the systems. I want to kind of do a count, actually. I want to say, yeah, so there you go. If I just look at the absolutes, that is just a great long list of 1,000 systems and how many per system got infected over that period of time. That's pretty good. And if you want to look at the densities, you can look at the other row or the other column, and that'll give you an idea of the saturation.
Nice.
Okay, but we also don't know the saturation of, we don't know the density of susceptibles in the first place. So we might measure that as well going in, so we can look at a change, right? Because this is only useful if we know how many planets were even susceptible in the first place. Okay, so, and we don't actually know right now what the distribution of the oxygen levels is empirically, but we know it from having generated it earlier on, right? Because we made a Gaussian, I think, in the last video that we made. So the atmospheric composition was, yeah, it had a Gaussian with a mean of 0.4, standard deviation of 0.2. So, yeah, so we kind of need to know per system. So,
does this array does this reflect back to the system? Like each of these 1,000 values, does it reflect back to the systems we created in the data frame? And only asking that to see if we can plot it.
We didn't extract it on a per planet basis because we only extracted system level information for that. So there's some.
So we generated the chart of systems. So this would it be difficult to maybe use a color map?
Yeah, that's good.
Yeah.
Right. So we could go back, and when we extract the table, we could have another column here that is the
percent.
It could be the percentage of susceptible planets. Great. That's a good idea. Yeah. So it gives us a chance to cycle back here and add some more instrumentation of things that become interesting.
And I think if we plot it and use the percent of infected planets as a way to go for intensity of a color or size of a bubble, that could be just an interesting way to have people look at it and say, oh,
that's right. That's right, because again, we'll be designing rules that we need to be able to visualize ourselves first. We're our own guinea pigs, as I think most game design really is, right? You have to constantly be playing it out yourself to see that it makes sense. So what's interesting about, we have to be a little careful, because on one hand, this function that we built before is meant to be, it was originally intended as a prototype of how you would extract the data from the object model to the eventual SQL database. So in one sense, that is meant to be pure, and it's meant to not add any derived data to the model. Now, temporarily, we may have to flag this in the comments or something to make sure that it's very clear. You don't want to give away some of that derived data. Some of that derived data is for us. Mm-hmm. Now, in fact, so I'm going to add a comment. I should really have put a doc string in here before. This is a utility function to extract table. Extract a table.
This almost feels like something you would want to make like a private. It's like something you don't surface, but use now.
Yeah, I mean, because we're in a notebook, actually, a really good way to do that is to just add a column to externally to that function, right? So you might still need a for loop again, but yeah, it's kind of an independent function. And you could write a function. You could sort of say maybe make a function called add diagnostic. Diagnostics to table. Oh, and that's to a data frame, really.
If you want some static, I'll take that one.
I'm good.
Being too polite.
So you want to?
It's going to set as if you want to put your foot on it, something that doesn't roll might be.
Oh.
Pardon the interruption. We're just doing a little.
I guess I'll
Intermission music.
Intermission.
Oh, yeah. Did we already have that question?
Yeah, I just responded in the. Profile pick. What's your question?
I'll start building this out while they're asking. So, let me know when they bring up the question. I will loop through the systems again and put in a measure of so I need for planet in sys.planets. I need to know, I need a count of, I'll write it out first and then I'm going to turn it into a list comprehension, I think, but I need to know if the planet oxygen level is above my oxythresh. So basically if if it is, then it's going to count the susceptible, and I'm going to count that up, right? So all right, I don't know what to do with that question.
Unplug it and plug it back in.
The susceptibles will, let's see, for planet, okay. We have none initially. USB receiver, yeah, I have no idea what that even is. Alright, so we obviously want a count of the susceptible planets, and that is, I guess I can just leave it as a for loop, spell it all out. But that's quite, I can write all of that in one line, which is kind of neat, and it would look like, first of all, I would need actually, what is a nice way? I could sum a list of things, or I could, first of all, let me drop that in. And then it'll be if. Yeah. So you would just drop in like a number like 1, and then you can do a sum over that. So that's a one-liner. Now, depending on how how readable someone thinks that is, I think that's actually pretty readable. I don't want 2 if statements there. Right, it's the sum of a list of the value 1 every time P for P in planets has the property that the oxygen is over that threshold. So that's pretty readable. In any case, I'll leave that as a comment. Don't need to do it twice. So for each system, so what I'm trying to build is I'm trying to build a new column in this data frame. So the end result, and data frames are mutable, so I can just call this column susceptible density, and it's going to be this value that we build.
How do data frames compare to structured people might be more familiar with?
Data frames are from a library called Pandas, and they are built on top of NumPy arrays. And so people are probably more familiar with NumPy arrays. The main thing is you can name these columns and rows in ways that NumPy arrays, you don't really do that. You just index them with integers. And then, of course, you have statistical functions and other sort of pivoting functions on these data frame objects. They're very similar to and I'm sure were inspired by the data frame class in R, which came first, and is, I think, inherent in R, whereas this is an add-on library in Python.
Take it way back, if you're looking at this and trying to get a feel for what's happening and what we mean by data frame, if you're familiar with working in Excel or seeing an Excel spreadsheet, just think of it as a list of features, a list of attributes, and then a list of observations. So it's basically your data frame is a spreadsheet, yeah. And we've built a model that sets up all these features across all these planets. Now, the amazing thing about Python and Pandas is so we have this universe, we have this, can you go to the map?
Oh yeah.
So yeah, this is a full array of planets here, and there's all these features that describe what these star systems are like, and we're able to, now that we've generated this universe, now we're trying to understand the properties, and we're actually trying to understand what it is, and we're using spreadsheets and data frames to do that. Python lets you get to that data really fast.
Thank you. That's good. All right, so I'm going to be building. I can assign a list of the right length to a column of the data frame. So there's going to be a value in this list called sus density for every system. And so I've done a count over the planets, and then for each system I'm going to append a value to that list, which is the total count that we came up with divided by the number of planets. Now, the other problem will be that sometimes there are no planets, and so I'll divide by 0. So yay, I need another conditional.
What happens if you divide by 0? Does that raise an error, or does okay?
Yep, 0 division error is an exception. But we also maybe need, we might need to indicate a nan, right? Because I can't not put something in this list because there has to be an entry for every position. So I'm just going to use a nan.
And how is that different from putting a 0?
Because you could have 0 susceptible planets out of a finite number of planets, and then you will also have a density of 0. So you wouldn't want to confound those two pieces of information, right? You want 0 to only mean that there are planets, but there are none of them that are susceptible. Whereas if there are no planets at all, that should be an entirely different kind of flag. All right. So now we have nans and we have densities, and we have the right number, and we should be able to assign that to, yeah. So let's see if we can do that. Oops. So I'm going to hit df with that. And that did something in place, so I actually have to display df, and there we go. However, I don't know that this looped correctly because I'm seeing nans for places where we have 4 planets. So I do not know what happened. Let's see. Ooh. I don't know for certain whether. Well, first of all, we need to double check that there are instances where there are. Yeah, there's one with 0 planets. Okay, so I'm possibly thinking that the order might not properly correspond to the order in the data frame. I'm a little confused for a minute, but a better way might be then to be, let's just be safe here, and let's actually iterate through the data frame itself. How did I? So let's check. Yeah, do you have?
If I can summarize, we were trying to imply, like we were using an
implied order. Yep. Yeah. And of course, it's always breaks on the assumptions, because clearly we're getting nans when there are finite numbers of planets, and so that should literally be impossible.
So we might want to consider names at this point.
Well, names is one way to decompose this, or maybe I didn't rerun. Sometimes what happens in notebooks is you edit things in different places and then you fail to rerun some of the cells. So let me remake.
You kind of have breadcrumbs, right, with the numbers beside it. So those numbers are the order in which things range.
Yeah, because if we reflect, right, my university table function also iterated for sys in uni, and so if I have consistency in my uni object and I again iterate through it, those orders are going to be the same, and the data frame will retain the order. Actually, is that true? Let me think about that. So when you make the data frame, we have made it from iterating through a row list, and that row list was itself iterated through the systems in uni. So the row list will be in the same order as the systems in uni, and they are being added in an incremental row. So yeah, all of those should be the same. So it's quite possible that I just didn't rerun that. Let me see. So I just hadn't refreshed my data. So my algorithm was fine. I needed to refresh my data frame. It was a stale data frame. All right, so there we go. So now we have densities added as an add-on. And that will allow us to do a couple of things. So first of all, it'll allow us to compare. So I should just put a head here.
Refresh my memory. How many years of observation is this? This is 5?
5 years, right. And I haven't even run the full 5 years yet. I just did the first 20 weeks.
Okay.
Just while I was testing. We can run it for the full 5 years and get some numbers out. I don't want to print this stuff anymore because we've kind of already determined that something correct is happening. But what we will want to do is we're going to want to take... it's going to take a bit longer to loop through all of those. We now have the densities per system. And some of these zeros are going to correspond to nans in the data frame, and that's where we can actually assign we can create a new data column called infected density, and it should just be, this was all created in order. Oh wait, no, these are time, no, they're not time, these are infected was per system again. So yeah, that should map. So now when you look at the F, you can see when you get 100% infection, right? So you might for instance take the ratio of the infected density to the susceptible density and see what the outcomes are. So for instance, this one, 20% ended up being infected, but 30% were susceptible. Okay, so you can see an outcome there. So that's something that we can plot, right? So we might make a plot that takes another derived value, which would be the ratio of infected density. Notice that you can autocomplete the column names, which is pretty neat.
I didn't know you could do that within quotes.
Yeah. And so there's your percentages per system. And so we can look at the stats of that. And it's easier to look at the stats of that if you use the describe function. So I love the describe function, but to use it, you kind of really want to have that. Actually, it's possible that pandas itself might have describe. No, it doesn't.
You can just do .describe it at the end.
Not if it's not a data frame. So this is a series. Actually, it's possible it does. Okay, good. Thank you. So when you divide two columns from data frames, you actually get a slightly different kind of object back. It's a series, pandas series object, which has slightly different properties, but it also shares a bunch with the data frames.
For those watching a series, just think about. So we said that data frames are very similar to spreadsheets. A series is similar to a column of values in the spreadsheet. So
right.
Look at the data frame above that has sysname X and Y. Each of those bold names is essentially the name of a series, and those combined together create the data frame.
That is correct. And if you really want to see, right, so the type of one of those columns is indeed a pandas series. So what I just brought up was the that's how you name the type for a series if you wanted to build one from scratch. And you can, if you shift tab in the lab notebook, you will bring up a little pop-up here, which gives you some of the docstring that you can scroll through, which is really nice. All right, so there you go.
Well, that was what was that keystroke again?
It's shift tab.
Shift tab. Okay.
At the end, yeah. So right now you can do it right there.
And everything you're showing me is going to help me work faster too.
Yeah, right. All right, so describe is a method of a series and a data frame object, and I put parens around that division of those two columns because of the. Do you guys know? If I don't, if I don't
Oh yeah, it would only.
don't put parens around it, then the binding of the method attribute here will bind directly to this object. And so it will describe that column first, and then it will attempt to divide that column by the describe output.
Run it and just show everybody what that will look like.
Yeah, you just get an error. Or you just get nans, because it doesn't know how to divide the column by what's essentially a data frame. It's sort of just a meaningless thing.
Yeah, if you're new to data frames, you're going to encounter a lot of errors and challenges with making sure that you're dealing with like objects and things with the same length.
That's right. That's right. Yeah, so it's a pain when you don't get an error, right? Silent failure is the worst.
That is true.
So, yeah, this is why you really want to build up... This is kind of why we're doing all of this. You want to build these things up very progressively and consciously so that you can always have a lot of insight into what's happening. Because it can be really hard to build tests for this kind of stuff, especially when you're exploring, right? That's the worst place to be for doing test-driven development, because you don't know what to be testing for yet. And so this is sort of defensive programming in a way, and building in little tests as you go. So
I want to add something, kind of one thing.
Please.
Like, yeah, when you're developing this stuff, there's a paranoia that you've done something wrong and that you run into those silent errors. So it is important, if you can, to work along with someone, so that you have another set of eyes to review what you're doing.
Yeah.
And you can, if you don't have anybody in your immediate vicinity, you can reach out online. You can reach out to somebody like me or us, and we'd be glad to help you with your code.
Rubber ducks are super effective, right?
Yep.
Saying it out loud will trigger different thoughts.
Yeah, and it's really hard to speak out loud to yourself in a room, at least consciously like that, as opposed to just mumbling things to yourself. But you can try. But I mean, really, yeah, having another person there is a really fantastic way to do it. All right. So next thing will be. So we've described this data set. So that tells us that we have 713 entries. Now, describe is kind of smart. What that means is there are 713 non-nan entries, right? 713 finite. So that should correspond to the number of systems that have non-zero planets.
That tallies up to 1,000-ish planets.
Well,
Exactly 1,000.
we haven't explicitly counted how many do not have planets.
Right, but the total number of planets in our model.
The only way that something would appear as a nan is if it didn't have planets, right?
Yeah.
So this kind of implicitly tells us.
Yeah. It's necessary. It has to be true that that's the count of systems with non-zero number of planets.
Right.
Yeah.
And we're generating 1,000 planets.
Right. So So it's about 70% have planets, and I don't know whether we had. Well, I'm not sure what statistics we used. I think we just had a random.
But it was 1,000 planets that we assigned out randomly to systems.
Sure, but if you look back at how we generated these systems, we were using a random integer between 0 and the max number of planets.
Right. Consuming total number of planets.
Right. So, but if you remember, the max num planets is actually can I shift tab this? I don't remember. No, I would have to do. So it's 10. Okay, so there's a 1 in. I think this is inclusive. I forgot. Yes, both endpoints. So there's a 1 in 11 chance that a system will have 0 planets.
You know, this is kind of funny. So if you think about it, the number of planets is going to have I'm guessing that the number of planets is going to correlate strongly with the infected percent in a negative way. So that if you have one planet and we set a minimum of one planet, like if it has a planet then it's infected, then those are naturally going to be 100%. Then your larger systems are going to have always show a lower. Well, be more likely to show a lower percentage.
Yeah, and we will have to build some measures of these things as we start to adjust the parameters more. But yeah, what it tells us is that 70% density across. This is essentially like doing the fact that these are meant to exist in the same universe is kind of irrelevant. What we've really done is we've taken a sample of 1,000 possible planetary systems and on the assumption that one random planet is initially infected, over 5 years with these parameters, how likely is that system to end up being infected? And the answer is 70% on average. But the standard deviation is quite large. Right, so the standard deviation is 30%. And so it's pretty infectious, right? So those are good kinds of diagnostics. Like you almost will end up building some kind of dashboard maybe to track consequences of changing parameters on these kind of larger scale outcomes. And that's one way that you might stand a chance of controlling some of the emergent aspects.
It's really important to be able to ask questions of your model, right? Rather than just generate a set of assumptions that you made early on.
Yep.
Because you will find things that you did not suspect, right? Instead of just monitoring and observability.
Yep. Yeah, indeed. Cool. So what do we want to do? What do we want to do from that?
So now so that's our spread diagnostic.
Mm-hmm.
And that is calculating distance or just distance of planets?
Wait, there's no distance right now, I don't think.
Well, we incorporated it in the planetary model, right?
Well, we talked about trying to leave that open, but right now we still only have these 0 to 9 integers.
Right, but that changes how infectious.
It does change how infectious it is, yeah. Right, it does, yeah.
Just at an inter-system level.
Yeah. You know what would be interesting is if we actually tracked these statistics through time. But, well, I guess it's actually not going to be that surprising because we don't have inter-system stuff.
Actually, I do kind of want to track it over time because on the current data frame, we're looking at 20 weeks, right?
Mm-hmm.
And in the 20 weeks, if you scroll down just a bit.
Well, no, we just did it for the whole.
Oh, we just did it for the whole.
We just did it for the whole 5 years.
Oh, then then it would be interesting, to plot that over time.
Well,
okay.
There's no interplay there, right? It's just these are just.
They're all isolated.
Yeah. But you'd still get to see kind of
systems that become infected.
Yeah, and you see the rate that it's happening and things like that.
Well, step one would be before you end up plotting it on a map, step one is just to get the data at all, and you could at least plot a graph of how many systems, asymptote to 100%.
So maybe graph by number of planets. That might be interesting.
Yeah, you might plot that per. Right, you might aggregate based on systems with that number of planets. Very good. Yeah. So good. Yeah. But capturing that through time is a lot harder. So, because you've got to record the state at all of those weak positions. And in a sense, that's what we might end up doing that anyway, if we want the time histories recorded for past data sets.
We could build a function or just a loop that iterates through the time period. So, yeah.
Mm-hmm. Yeah. So I guess we do need to build that.
Kind of the point of the whole thing, right?
Yeah. I mean, that's assuming that this infected value is something that we expose as a primary piece of data, as opposed to something that we're just using diagnostically internally. Wow. But in any case, there will be, if it's not this, it will be something else that we will create like this, that we will want to expose.
I'm going to be a party pooper. Mm-hmm. So it is 5:03. So we're coming to time. But I think that it would be a good little piece of meat if we... Ooh, that sounds terrible. Strike that from... I think it would be good if we did... take one of these observations or take one of these diagnostics and visualize it, just because that's so, like, we've been doing some visualizations. Just want to.
Okay. So how about plotting the distribution of planets that actually have, systems that actually have planets? That's an easy place to start, which is just basically adding color or size to these dots. Okay, so. Maybe on the side you could help me look up to remember. There is a way, I think, with these matplotlib calls that you can pass an array for the marker size attribute. So when you plot this here, I think you can say marker size. Certainly, you can say it's a constant, right? So
Can't you just set it to the name of the column?
oh, maybe you can't. Yeah, that's what I was probably going to do, but
So just basically what that variable name is.
I forget whether you can do this. Oh, there might actually be. We need to look it up for pandas
Those are the types.
data frames.
Yeah, they have. Okay, I'll do plotting.
So there might be an additional thing that you can pass that has other properties in it. I've forgotten. We might also not use. Let's think, because I've done this before, but I don't have an example handy to remind myself. I'll just try using the axes plot directly, and I'll pull out dfx and against dfy coordinates, and then my style is going to be
You can certainly pass an array to.
I just don't know whether you can pass it to axes plot. I guess I can find out.
If you do df.scatter, like if you do just the data frame .scatter, then size is it's s equals basically s equals then the
right,
column
scrap.
name.
But is that for the entire?
No, I think you can select. Wait, no, it doesn't have a scatter. Doesn't seem to be a method of this data frame.
So I think that's what this is saying is.
They're looking some stuff up.
Scatter's not a method of that's.
No, unless it's a pandas.
I'm gonna try it out on another set of data.
Yeah. All right. Let's go back to my basic for a minute. So it doesn't take a list, right? So you can't pass to matplotlib. Oh, well that's all right. We'll do it this way. So the scatter is it's a matplotlib function, and apparently that one will also work. So scrap that. We'll use. There we go.
You got it already?
Yeah, it's a matplotlib thing.
I'm gonna see if it works in the data frame because I was looking at the pandas documentation.
Okay. So I think then that's where I can pass.
You're right.
So the parameter seems to be marker. Okay. Oops. Nope, I blew it.
It's very forgiving.
So when I was a kid, there was no undo button, and it was always just very depressing. Too many parens.
Dad tells stories of people trying to get their punch card programs together. It's a bad time if you drop them.
Yep. Yeah, I know people who've done that. So I'm still doing something wrong. I'm not reading this instruction correctly.
I did not check for date either.
It looks like. Oh yeah, right. It could also be out of date, but no, I think I'm just doing it wrong. The marker. Ooh, it's a dictionary. Yeah, I need to read this more carefully. I'm sure I've done a scatter plot where you just pass in the data like that, but never mind. So they have a dictionary, and it's keyed by kind, but kind. Oh, that's not the size though.
Right.
Oh, the size.
Yes,
Oh, it's S. Okay, it's S. Let's try that again. So I might have to. Oh, I keep putting too many parens. Okay, so S cannot. Yeah, I'm not sure I'm understanding this example.
So the S is looking for some absolute value. Interesting. Multiple values.
Yeah, so this isn't showing that you can. This is for different types of marker, but not marker sizes. So what I want is one marker, but to change the size. I have done it before.
Yeah.
But the trouble with these things is there's about usually 3 different ways to do it, and you can never quite remember the right combination of pieces.
So m.weight to have a different range.
You're looking at the same thing I'm looking at, right? Is that the same one that you were just showing me?
Yep.
But that one assumed plt.scatter and oh, that is plt. Yeah, so
If you look down here,
Let's try something like variable marker size.
so it's just, so it's basically weighting it, setting the size.
ah.
Yeah, the thing the scatter function says up front that it's for things that where the markers don't vary in size.
So what they were doing is basically using different markers, but then scaling those different markers, right? So they are.
How are they scaling the markers though?
So you can set the scale per marker. So they're different markers, right? It's a hack, right?
Yeah, that's a hack, but we don't have enough markers. Like we want one marker. I've absolutely done this, but yeah, it might not be with Matplotlib. It might be through Seaborn or something else.
So what you end up getting is something like this, where your squares are big, which your circles are small.
Right. Yeah, I think the Seaborn scatter plot might be what I used in the past. Sizes. I have a feeling that's what it would be. So list, dict, or tuple. An object that determines how sizes are chosen. Yeah, let's see.
Are you using SNS right now?
I will, yeah. I think I haven't imported it yet, so I'll jump up. Alright, let's try this again. What's it called? Scatter plot, there we go.
It's fun.
Sizes. So let's just get the syntax to work. There we go. Alright, now they are all the same size. Now let me make an array that is an A range that is len_df. Wait, see, oh, oops. Nope, that didn't give me different sizes. Unless...
Is it the scale? Like does it scale up enough to notice?
Yeah, that's possible, but there's 1,000 of them, so you'd think that would be enough. When size is numeric, it can also be a tuple specifying... I might be reading this wrong. I don't know what it means by sizes. Size, name of variables. Grouping variable that will produce points with different sizes. Still a little unclear what they mean by sizes. Oh, there we go. Oh, okay. You can pass a data frame. Nice. Okay, Seaborn's smart like this. You can pass a data frame instead of the data itself, and then the X and Y can just be the names of the columns, and then my size can be another name of another column. Now, that is pretty cool.
I actually just I used that on another data frame. I don't know. I can't share my screen though, but yeah, you're definitely going the right place.
Yeah. So sizes then will be, I guess we'll call it, for a start we can just call it num_planets. Right?
You could let me look at your code again.
We just need to assign. We need to create a number of planets column and add that, which is easy.
So let's try it with df.susceptible density. Size s equals.
Oh, sure. That's a good point. We actually have a proxy for that already. Susceptible density. Now, the trouble will be that needs scaling because those numbers are between 0 and 1, and I don't know if we can. I don't know how we would do that. I think you'll find that will be a problem. Yeah, because there's not enough range for those marker sizes to show a difference. So, but that's still useful because what we'll do instead is we'll just.
So S is the same.
Oh wait, that's susceptible density, which is also a measure of planets that have an oxygen level. In any case, we want to be able to multiply that. You know, I'm going to try substituting this in and just multiplying it by a factor. No. Yeah, it's not picking up the sizes.
Is sizes the same as S?
Oh, sorry. I blew it again. It's size, not sizes. Never mind. See, again, silent failure. So the trouble is you can pass in keyword arguments, arbitrary keyword arguments. And because that's so flexible, it just lets you pass in anything you want.
It's a feature.
It's a feature.
So what do we get here?
Well, this is now giving you an idea.
Well, there we go. And look at that. I didn't realize that Seaborn actually has a legend for the size too.
Yeah, it's pretty nice. Now, of course, the scale is completely wrong, right? In fact, what we really probably would want to do is maybe multiply it by 100 and call it a percentage. But
Let's do it.
I don't know whether it rescales the sizes to not be stupid, but some of these dots might be good for it.
We'll see how smart Seaborn is.
I don't know why it doesn't understand that it could go. Could only go up to 100, but that doesn't matter. But yeah, that gives you an idea of how selecting the Gaussian for both the Gaussian for distribution of oxygen and then the threshold that you use to measure susceptibility impacts the geographic distribution. Because now you could do statistics on, having susceptible systems and how likely are they to be within some radius of each other in cluster.
And also think about where, like if you're plotting like this, if you're making your star systems appear larger, not based on the actual size of the star system, but it's based on the likelihood that it has a plague. It's just a different way of looking at size in the galaxy.
Mm-hmm. Yeah, you can substitute other things in there for sure. Yeah, so that's pretty neat. So we've taken a step forward. So I guess next time we'll come back and add some additional diagnostics and start to think more about some of the mechanisms that we're talking about with spread. System to system spread, and charting out time courses of events through systems, so that we can maybe even animate this picture and see how it, we can put weeks at the bottom and watch it play through in time and actually visualize some forms of spreading and then do statistics on that as you change some of the parameters for our model and get a feel for what's going to generate data that has a good feel.
Are we able to animate directly within Matplotlib, or will that...
You can. I've done it a bunch of different times in different ways. There are hacky ways and better ways, and I'll do some research in the meantime to make sure we can pull up something that will look pretty good.
Stay tuned for an answer.
Yeah, stay tuned for an answer. Thank you. Yeah, I hope that was fun. I'll see you guys next time.